Hi everyone. In this video, we're discussing problem number 733. The problem name is Flat Fill. It's a problem from Leetcode. It's an easy level problem from Leetcode. So let's read the problem statement. Here they have given quite a lot of information. So let's read the details one by one. The first thing given here is an image, which is basically an m by n integer grid. It's a matrix basically, right? So image is a matrix, right? And in every cell, the pixel value of the image is given, okay? So that is one information. And we're also given three integers. The first thing is SR. I look at it like starting row. And the next integer is SC. Again, I look at it like starting column. And a new color. That is also an integer, right? So we will discuss that. What role they are playing in this problem, we will discuss. Now we are supposed to perform a flat fill. I'll explain what it means. On the given image, the given image is basically a matrix, right? So we have to perform the flat fill on the given image, starting from the given pixel. Okay, we have to start at the pixel SR, SC, right? SR is an integer, SC is an integer. For example, SR is say 3 and SC is 5. Then we have to start this flat fill process at that particular cell 3, 5, right? Now to perform flat fill, what are we supposed to do? We need to consider the starting pixel. So starting pixel is what is given in terms of SR, SC, okay? So that is a starting pixel, right? Now if you find any pixel that is adjacent to the starting pixel, and by adjacent I mean it is adjacent to the left, like the immediate left or the immediate right or the immediate top or the immediate bottom. Okay, so these four cells which are connected to the given cell in any one of these four directions, up, down, left, right, right? So that is what they mean by saying that, okay, any pixel connected four directionally, in the sense up, down, left, right. So if there is any cell which is connected to the starting cell four directionally, and also it is having the same color as that of the starting pixel, then we change the color to whatever is the new color suggested. By the way, here color means just a number. It's not like we are literally dealing with colors. We are using numbers as substitute for colors, right? So let's check this example. Example number 1. So you can see this is the image given, and you can clearly see that every single cell is either 0 or 1. Let's assume that 0 represents one color and 1 represents another color. So every single cell is either 0 or 1. You may even have multiple colors, right? So they didn't say anything about it, okay? So we have this particular image, right? A 3 by 3 matrix, technically, right? And SR is given to be 1. SC is also given to be 1, which means we have to start this process of flat filling at this particular cell 1, 1. Right? We have to start at this particular cell 1, 1. Please understand everything is 0 indexed. So it is going to be 0th row, first row, second row, 0th column, first column, second column. So 1, 1 is over here, right? Everything is 0 indexed. Okay. So this is where we start this process, and we will check all the four directions, up, down, left, right. And if any of these four adjacent cells have the same color as that of the starting pixel, then we will change those adjacent cells also to the new color. Here the suggested new color is number 2. So you can clearly see this is where we are starting. We are changing this 1 to 2, and we are looking at the immediate top, bottom, left, right. Out of these four adjacent cells, only this and this, they have the same color as that of the original cell, right? So we convert both of them to 2. The new color is 2. Again, repeat the process. Repeat the process as long as we can find adjacent cells having the same color as that of the starting cell. And once we exhaust all possible cells that can be reached in any one of these four directions, up, down, left, right, then we are done with the process. Let's now quickly head over to whiteboard, where we have one more example, and using this example we'll understand the problem better, and we'll come up with an idea, an algorithm to solve this particular problem, right? So here this is the given image matrix. So this one is the given image matrix. It's a matrix of order 4 by 4, So there are 4 rows and 4 columns. It's not necessary that it has to be a square matrix. It can be a typical rectangular matrix. Okay. Here let SR be 2 and SA be 1 and the new color be say 5. I just chose a number which is not there in this particular grid. Okay. It can be 5, 6, anything, doesn't matter. Okay. So where is this particular cell? SR is 2 and SE is 1. So it is the second row, 0th row, first row, second row. And SE is 1 means it's the first column, 0th column, first column. So SR comma SE is right here, right? This is SR comma SE. Now what are we supposed to do? How this flat fill logic works? So this is the given cell. This is the starting cell. Whatever is its color, here it happens to be 1. It can be any color, right? Like I told you before, colors are nothing but numbers here. In this particular problem, we are not actually dealing with the colors. So whatever happens to be its color, in this case, the color 1, we will be checking all the 4 pixels which are adjacent to it. Up, down, left, right. And out of these 4 pixels, out of these 4 adjacent cells, whichever happens to have the same color as that of the starting one, we will change it to the new color. We will change it to new color, right? Okay, so first we will have to change this itself to color 5, right? We are going to change it to what? Color 5. I'll put 5 here, right? And out of these 4 adjacent cells, this one is having a different color, so we can't do anything about it. This one is having the same color, so we will have to change it to color 5, right? And this one is having the same color, we will have to change it to color 5. Even this one is having same color, we will have to change it to color 5. Right? You see, the way I'm filling out all these colors is more or less like BFS technique, BFS algorithm, breadth first search algorithm. Whereas when I'm actually coding it out, I'm going to use DFS, depth first search algorithm, because that particular code is a bit more elegant compared to BFS. Like we don't have to create while loop and a queue and stuff. You know, it's not that complex to write. So I'm not saying that BFS is anything very complicated, but DFS will be an elegant solution in this problem at least. So yeah, so we are done with this. Now take this particular cell. What are its adjacent cells? 2, 1 and 1. This 1 is already seen. We have already visited. In fact, this is where we started. So while coding, we have to make sure that we create a set to note down all the cells that we have already visited so that we don't revisit things and get ourselves in an infinite loop, right? And that is something we definitely ensure that we are going to include in our code. Okay, so this is done. So 2 is a different color. So we can't do anything about it. Okay, you check this particular cell. It is having same color as that of this one. So we will change it to color 5. Now look at this one's adjacent cells. It is this, this and this. This is already visited. This is a different color. So this is the only other option. Okay, change it to color 5. Now, what about this one's adjacent cells? It is 2, 2, 0. These are all technically different colors and 1 is already visited. So this particular thing is like dead end. Beyond this point, you cannot go anywhere. What about this one's adjacent cells? 1, which is already visited, and 2 and 0, they're all different colors, so we can't do anything. So this is also like dead end. In the sense, it'll be in the graph, it'll be the leaf node. You cannot go beyond this point. Okay, so let's continue our journey with this only, right? So what are its adjacent cells? This is visited and this one is new. Okay, so we'll visit it and then change the color to this. And that's it. We can't do anything beyond this point. Okay, what are this one's adjacent colors, adjacent cells? I mean, this one that is visited. What about this one? That is different color. We can't do anything. What about this one? That's a different color. We can't do anything. There it ends. That's it. There it ends. We have few more ones, but there is no way we can reach this particular cell or this particular cell starting here and only by moving up, down, left, right. There is no way we can reach these two cells, even though they have the same color as that of the original cell, the starting cell, I mean, right? So there is no way of reaching this. So that is all. Our algorithm stops here, right? So how to code this? Let's see. The first thing that we're going to do is, let's get the row number, how many rows are there. That can be obtained by using this length function. It is length of image. That will give us the number of rows. and we denote the number of rows by the variable m, and let n denote the number of columns. And how do we obtain that? Length of image of 0. Basically, image is what? List of lists, right? So it is length of image of 0 that will give us the number of columns that I denote by n. And starting row and starting column will be given, right? Okay. And whatever is the color in that particular cell given by the starting row SR, SC, okay, that is our original color, or let me call it old color. Since they are using the variable new color, I prefer calling that one as old color, right? So what is old color? It is the color at SR, SC. Now, how do we write it in Python? Image of SR, SC. This is the old color. And like I told you, we need to introduce a set, an empty set. Initially, it will be empty. Okay. Let's name it visited. This is where we are going to keep track of all the cells that we have already visited, right? So that we don't get ourselves in a loop, right? Okay, so this is one empty set. We name it visited. So this is where we are defining a function, and we are defining it recursively. And our code is basically a DFS code, depth first search algorithm. Okay, you can look at it like a graph problem. Okay, and we are going to come up with a DFS solution. Okay, so let's call the function fill, which is going to take in two parameters. I call it x, y. You will have to imagine it to be like x denotes the row number and y denotes the column number. So we define a function fill, and it takes parameters x, y, right? Now, even to apply this function, we have to first make sure that the certain conditions are true. What is it? Number one, the row number, which is x, must be greater than -1. In the sense that I'm indirectly telling you, it must be at least 0. It can't be negative, right? So that is what we achieve here by, imposing this inequality. And it must be less than m. M is the total number of rows in the given matrix, which is called as image, right? So this condition must be true. If it is not true, then it means that we are going out of this matrix, right? Which we are not allowed to do. Okay, we cannot go out of this matrix. Okay, so any traversal should be happening within this matrix itself. Okay, so we will have to impose this condition, and we impose a similar condition on y variable, right? It must be obeying this inequality. -1 less than y less than n. Y denotes the column number, right? So it has to be at least 0. And at the same time, it has to be less than the total number of columns in the given matrix. That is another condition. And we can perform this flat fill only if the adjacent cell is having the same color as that of the given cell, right? So we have to make sure that image of x, y is equal to old color. Old color is the name we have given for the color that we noted down in the starting row, starting column, in the very first starting cell. Whatever is the color, that color is what we are referring to as old color. So we can even apply this particular algorithm provided the color in that particular row, that particular column, in that particular cell, the color is exactly same as that of the starting cell's color. So that is why we are imposing this condition. And one more condition, x, y, the tuple x, y is not in the visited set, because if it is in visited set, then we have to avoid considering that particular node or that particular cell. There is no point. It will put us in a loop. So if it is not visited, only then we will think of applying this following algorithm, not otherwise. Okay, so if all those conditions are met, so what are the conditions? The row number x is a valid row number. That is what we are conveying here. The column number y is a valid column number. That is what we are conveying here. So these two conditions put together will ensure that we are always traversing within this matrix only, right? Within this image only, right? And this particular condition means that the cell under consideration is having the same color as that of the starting cell, which we are denoting by the variable old color. And this particular condition means that the cell under consideration is not already visited. It's a fresh cell. First time we are processing it. Okay. So if all these conditions are met, then what are we supposed to do? the first thing that we are supposed to do is to change this color at that particular cell given by x comma y, change that color to new color. Okay, so how do we achieve that? Simply overwrite image of x comma y is equal to new color. We simply overwrite the existing color, right? So it's equal to the new color. Okay, that is one thing. What is the very next thing that we are supposed to do? Make sure that we are adding this tuple x comma y to this particular visited set. Okay, so visited dot add of x comma y. And once we are done with these two, we will have to explore the adjacent cells. And it has been very clearly stated what is the meaning of adjacent cells. Cells that are adjacent 4 directionally, up, down, left, right. Okay, so we will have to now call this same function within this function itself. So how do we do that? It is fill of what will be the coordinates of the cell which is to the immediate right, that is x plus 1 comma y. What will be the cell to the immediate left? It is x minus 1 comma y. What will be the cell which is right on top of the given cell? X comma y plus 1. And what is the cell which is right below the given cell, which is x comma y minus 1? Okay, so here what are we doing? We are exploring all the 4 adjacent cells. And finally, of course, we will have to actually call this function outside of its definition. We have to call it once. Fill of sr comma sc, because sr comma sc is the actual coordinates given in the problem, sr comma sc. Okay, and once we call this function, we will have to simply return the image, the matrix, which is now modified. We have modified the matrix in place, right? Okay, now let's see how it works. Let's actually code it out. What is the first thing that we're supposed to do? Get the row, number of rows in the given matrix, that we denote by m, and get the number of columns in the given matrix, that is obtained like this. N is equal to length of image of 0. Okay, and then we define something called as old color, which is the color at this particular coordinates sr comma sc. Sr and sc are integers given as inputs. Okay, then also we need to initialize an empty set in order to keep track of the nodes or the cells that we have visited. And right now we are creating that function. Okay, we call that function fill with exactly 2 parameters, x comma y. That x parameter, you can look at it like the row number, and the y parameter, you can look at it like the column number. And we have to first of all subject it to certain conditions even before we think of applying this function. What are those conditions? Make sure that the row number is valid. This inequality basically ensures that. And make sure that the column number is valid. This inequality will ensure that. And make sure that the color at that particular cell, x comma y, is old color. And finally, also make sure that x comma y, that particular cell, is not in visited, right? If all these conditions are met, the first thing that we're going to do is overwrite the color. Image of x comma y is new color. So this is how we overwrite the color. And then make sure that this particular coordinates x comma y is added to the visited nodes or visited cell. It's added there. Let's make sure that. Okay, so visited dot add, we are adding the tuple x comma y. And once we are done with that, we will call this function within itself. Okay, so that is obviously why it is called as recursive function. Okay, this is the cell. We are exploring all the adjacent cells. This is the cell to the immediate right. This is the one to the immediate left. This is the one which is right above. And this is the one which is right below. Okay, so we are exploring all the 4 adjacent cells, and this is basically a depth first search algorithm, right? Because this is where we define the function. And once all the conditions are met and once we are done with the job, we will first call its immediate right. And that function will now get executed. And within that function, you will call its immediate right. And in that layer, you will go another layer deep. You call its immediate right. It goes on till you can never find any immediate right. That is when you keep calling immediate left. Till you can keep calling immediate left, you keep calling immediate left. Okay, till you exhaust all possible cases. And that is when you go for the one which is right above. And once you exhaust that possibility, only then you go for the ones that are right below. Okay, so this is a DFS algorithm. Okay, so after that, this is only the definition of function, and this is where we are going to actually call the function by using the actual coordinates SR, SC, right? So this is where we run the function recursively by calling it outside the definition. And finally, we return the image, which is the list of lists. And we have modified this image matrix in place. We didn't create any new matrix. We have modified it in place. So let's run our code, run our code to see how it performs. Okay, fine. One test case clear. So let's actually submit the code to see how it performs in all the test cases. Good, our solution is accepted, and also our runtime is pretty decent, just that the memory usage is not that very good. So we'll think about it later. And I hope this particular solution is clear. Thank you for watching.